I am Manash Goswami, and I have my colleague Kitty here with me from Microsoft. I'm from the AI platforms team. We work on building the tools that you use to develop machine learning solutions. And specifically, I'm responsible for looking after accelerating machine learning models on different types of hardware. So I'm going to talk a little bit about how you can build ML applications, and then how you deploy them and execute them across a variety of endpoints, specifically with ARM devices on the edge. We will do that by using a high-performance inference engine called ONNX Runtime, and I'm going to describe a little bit about that as well. You can keep them. You know, looks good. But before we jump in, I want to take a step back and say why now. I think you heard a little bit about why now, and our perspective of why now starts with the proliferation of cloud. With the access to, theoretically infinite compute and infinite memory, you now are able to process a lot of data. And that means that all the AI work that had started and was invented, in the past decades now can really be used. You can retrain on algorithms, you can develop new ones, and then you can deploy them. The second innovation that's happened is the notion of having these IoT endpoints, that is, these electronic devices which are collecting data from the environment, and now with connectivity, they are ingesting that data to the cloud. This gives rise to like large training workloads where you can use large data sets to build your ML application. This then gives us the notion that you now have an edge where you have a lot of intelligence and you also have a lot of access to data, which is where we come to today about using AI at these endpoints. When you look at some common examples, and we talked about a few in the earlier sessions, it's important to look at how you can process data on the edge or place where it's captured. This is important for a couple of reasons. One is can be real time. You need very instantaneous input or insights into what's happening on the edge. A good example is, we always talk about autonomous driving. But an even interesting example is think about a particle accelerator in physics. When you're running an experiment, you're generating so much data, you need to be able to process and capture only things that you really need. And that it's physically not possible to store all the data and process it in the cloud because there isn't just enough time. So the true real-time processing applications like autonomous driving, like particle acceleration in large physics experiments are scenarios where you really need high-performance computing right on the edge. The other aspect is anonymizing data. We see a lot of scenarios where privacy is important to protect. We respect that. We want to enable that. And with delivering AI solutions where you can execute some logic, some algorithm, where you can completely anonymize the data and yet get the telemetry to make use in your business application, that's really important. That's an example of how our retail partners use intelligent edge solutions to manage inventory, whereby they can preserve the privacy of the retail store, but yet have a very efficient operations by updating and understanding and measuring how they need to manage their operations. So we look at this in two ways at Microsoft. The cloud enables you to build intelligent applications, but then the edge is really important to go deploy this. And we call this the intelligent edge. The intelligent edge is a spectrum of devices where you will be processing data much, much closer to where the data is collected, right? This edge spectrum can be quite broad. You have on one side very, very tiny sensors powered by M-class microprocessors and microcontrollers. On the other side, you have got custom neural network processors that are used as co-processors in heavier equipment. The compute environments are very different. And on one side, you have hardware capabilities which are, compute and storage constrained, connectivity constrained in some cases, in most cases. There is no real high-level OS. And both sides of this graph are like opposites of each other. The OS environment is mostly embedded or real-time OSs, and there literally is no acceleration capability to execute the ML algorithm in a macro level or in a single kernel. And on the other side, you have compute environments where you can run containers. You have a higher level OS like Windows or Linux or even maybe Android. And you can actually distinguish what parts of a model need to be accelerated versus parts which can run on a generic compute. So this spectrum means that the AI development environment needs to be able to address and be capable of targeting all of these. So let me walk you through how we look at the ML development workflow and how this actually can then help support an environment of the intelligent edge. If all of you are here, you're probably interested or are developing AI applications. And one of the most important things about AI applications is getting the data, organizing the data, which means that the very first step that you have in your end-to-end workflow is about preparing your data. Once you have prepared your data, you now need to build your experiment, which then will generate the custom algorithm, the machine learning model, the deep neural network model, or whatever else that you would have in terms of logic around it. So this training phase typically happens in the cloud. This is where you are going to build a model, and then you're going to test that model. You'll have to have some test data from your original data set that you'll use to validate if your model is actually behaving and producing the results and the predictions that you expect, because it needs to be useful for your business. Once that model is now final and validated, you would register it in your registry and then hand this over to the deployment side of your infrastructure to go deploy it at scale across a variety of devices. At a high level, this sounds very nice. It looks like a clean slide. It's a nice workflow. But there are complexities to it. When you look at machine learning for the edge scenarios are rarely similar to how you would test and validate in the cloud. You may collect data from the edge. You would train on the cloud. But what you would build is essentially a model that you would have validated in the cloud. Environments on the edge will be very different. Not only are the compute environments different, so your processing latencies may be different, but also the physical environment where you're getting the real data may not actually result in the kind of accuracies or the results that you need. So again, walking through the, I didn't realize this was animated. Okay, so here's what I wanted to say. So now once you have built your model, you now have deployed it to the edge, you realize that you now are actually in an edge lifecycle of the machine learning workflow. And in this, you would once deploy the model, you may need to collect some data when you're in production to understand if your seed model that you created in the cloud is actually valid. This data can then be used to retrain for that local environment. You retrain the model on the edge, and then you redeploy the model and then upload that artifact back to the cloud so that now you're able to manage and do some versioning of what specific subversion of the model that you used in your infrastructure that you now can use to retrain or even learn something or change something in your data preparation step. And then finally, of course, the monitoring step where you're going to monitor the accuracy of the model, monitor the performance of how the data is being processed, what kind of latencies you're reaching, are you hitting some compute or memory thresholds because you're running something really, really heavy. This is really important. All of these things are important, especially when you're trying to deploy AI solutions at scale. And it's not just building a model and testing it on one endpoint and back. Looks like I need to raise my hand to switch the cloud. So in terms of enabling you to do all of this, we work and build products and services that help you take models, either models that you have from other sources where you have built offline. You may build models in Azure, or you may have your own services and solutions where you are generating your own algorithms in your custom infrastructure. But the idea is that once you have built the model, you're now able to deploy this model through the pipeline that we have at Azure Machine Learning. And I'll go through this a little bit for the edge in the next few slides. The pipeline, as we talked about in ML workflow, requires you to collect data, train, and do the inferencing and deployment, right? This is your workflow for research to production. Hopefully you got that by now. But there are challenges. And we know these challenges because there are two parts of the organization or expertise that are required. The first half of this chart requires someone with deep data science experience, where you are actually able to process the data and then build a training algorithm which can use that training data to generate your model. And then the second half of this is where you have the engineering workflow. Some people call it the DevOps, some people call it machine learning engineering. But essentially, this is the workflow where once you have a model, you need to build your custom logic and custom application logic, which you can then deploy into your business application. This has challenges. How we know this? We use machine learning at Microsoft. And it's our organization that supports all of these products to deploy ML at scale. Most of these products deploy ML both in the cloud and in the edge. And the problem is that when you are building a machine learning solution, you are rarely working with one framework going into one compute endpoint. Training is done on a variety of different tool chains. You could be using TensorFlow or PyTorch or anything else that your data scientist may be familiar with or that he used in his grad school. And then when you look at the deployment side in production, these same models now need to be deployed across different types of environments in the cloud and the edge with CPUs, GPUs, NPUs, DSPs, and whatever else that the hardware ecosystem comes up with. But guess what? The data science world rarely understands what happens in the execution environment. And this becomes a real problem when you're trying to stitch together solutions which require models from different training frameworks. You may have a people identifier that was trained in TensorFlow. And then you use that outcome of that model and then feed that input into another model to detect gender. And that might have been trained in PyTorch. Once you're trying to deploy this application into one environment on the device, then you would run into some problems if you have to manage multiple runtimes which have their own execution stack. We believe that ONNX is capable of solving this. And ONNX stands for Open Neural Network Exchange. What this does is it enables us to take models that are trained in any framework and represent it in a common graph format, which can then be executed across different types of hardware. So once you go from training to production or inferencing, ONNX enables us to translate and get to a uniform representation of the graph. ONNX is an interoperable framework which is public, it's open source, and it is essentially a graph representation with which uses the compute nodes. It's a graph of the compute nodes with protobuf. It supports both DNNs as well as ML, traditional machine learning, and we are fully backward compatible in terms of versioning as the spec gets revised. As PyTorch and TensorFlow and others update with new ops, ONNX keeps revising to make sure that we support those. ONNX is convertible from all of these frameworks. So if you are using any of the popular training algorithms, then you are able to bring that model to ONNX. And then finally, ONNX was originally started by Facebook, Amazon, and Microsoft together. There is now broad industry adoption. And finally, as of earlier or last month, ONNX is now part of the Linux Foundation, Linux AI Foundation. So what this tells us is that ONNX is now a growing community, and at Microsoft, we are a true believer that ONNX enables us to go from training to inferencing in a seamless way and in a scalable way. So we talked about the workflow. What we do now is that once you have a trained model, before you go into your inferencing step, we would do a conversion of the ONNX model to ONNX, which then enables us to get to a uniform layer representation of the model. This This is required to then run the model across different types of hardware endpoints. This slide is going to be public. So here is a couple of examples of how you can get ONNX models. There is an ONNX model zoo. You can get pre-trained models from there to try out. Then you can also get ONNX models from your training experiments in Azure Custom Vision or using AutoML. And then finally, you can take any of the open source converters and convert your model on your own as well. The converters that are available are for both TensorFlow and PyTorch, but also Keras, scikit-learn, anything else that you have in your training environment. So once we now have the model in ONNX, how do we deploy it in production and at scale? Because this is the interesting part. If you're here from and part of the ARM AIoT Summit, then you would be interested in how we execute the model, right? So I will assume that the training part is all of that is taken care of now, and then when we go into inferencing an ONNX model, we do that by using something called the ONNX Runtime. The ONNX Runtime is an open source inference engine which is used to execute ONNX models. It is available in C, C++, and Python with Python APIs, and it's available and capable of executing across Mac, Windows, and Linux, of course. The ONNX Runtime can run on ARM, specifically with the ARM compute library, as well as on other architectures, right? We support an extensible format for supporting acceleration across the different types of compute endpoints. So what is the ONNX Runtime? At a high level, the ONNX Runtime is a graph parser which parses an ONNX graph to do any kind of optimization. The optimizations can be fusing nodes, as well as pruning the graph into specific execution blocks. The second part of this runtime is essentially interfacing with the underlying hardware. So given that the ONNX Runtime could be deployed in different kinds of hardware endpoints, the runtime has the ability, and with, of course, prior integration that we would do with the hardware partner, to actually plug in to a specific library called the execution provider. And what I show here below are a family or a subset of execution providers that already exist. For example, there's a default CPU execution engine, so that if you provided a graph which cannot be executed by any of the underlying nodes, it'll always fall back to CPU. So at minimum, you're able to execute the ONNX graph. But then we work with different types of hardware partners, like ARM, with Intel OpenVINO, and with NVIDIA across both CUDA and TensorRT. And of course, there are other libraries as well, like ngraph, MKLDN, and ROCm, and others. So the goal here is that with ONNX Runtime now, we abstract out the hardware-specific libraries that would be required to execute neural network kernels. And we take on the burden of pre-integrating and testing and validating with the hardware environment, so that you as a developer, you can write your application code to one API and then deploy it to the endpoint using ONNX Runtime, which then takes care of the execution part of the logic. In terms of supported architecture, we already talked about it. We support both CPUs, GPUs, NPUs, and across Windows, Linux, and Mac. So now, once you have built out the environment to run your inferencing, how do we go about deploying it? One of the assumptions I'm making here is that the deployment architecture for endpoints fundamentally today, in most IoT cases, use containers. As you look at the evolution and going into Cortex M-class processors, the assumption we are making is that those devices are so compute constrained, they cannot run containers. But there has to be a higher order node at the edge of the network, which is connected to the cloud. And that endpoint is actually running the container. So containers become the vehicle of communication between what your training infrastructure and what you have in cloud in terms of management, down to the edge of the network, which then distributes the workload across the different leaf nodes that you may have in your deployment. So the environment that you have for different types of hardware endpoints enables you to run different things as it relates to AI. AI requires three key functionalities. One is the ability to manage data, collect data, and prepare the data. You need to be able to run training on that data, and then finally inferencing. When you look at the hyperscale cloud infrastructure that's out there, and that's not just a specific statement of Microsoft, the cloud is capable of running all of the, managing and doing a lot of the workloads for inferencing, training, as well as data, or data inferencing and training, right, in that order. But when you go from one side to the other, the capabilities actually reduce. So at the other extreme, the sensor class devices can collect data, and then you would be able to run some inferencing on it. But more than likely, you are not going to be able to do any kind of training there because training requires much more compute intense processing. When you look at the middle of this chart, this is where things become really interesting. These are the devices which are running containers. They have high-level OSs, but yet these are devices that are sitting on-prem. These are devices which connect to the cloud. They're managed from the cloud from a control plane standpoint, but this is where most of the edge processing happen. And we believe that a lot of the AI-related workloads, specifically data preparation, training, as well as inferencing, can happen here, and we do have partners who are deploying workloads in those kind of devices. So how do we go about deploying them? So once you have built your model and you have created your final trained model and application, you convert it to ONNX, and then you deploy it with containers across any of these endpoints. Once you have a container, you are now able to deploy that container into any of the container supported environments that are out there. It could be VMs in Azure. It could be a generic Ubuntu VM or a Windows VM. Or if you have on-prem devices, like a gateway or an edge device from ARM, you could be, as long as the device is running a container environment, now you're able to get a portable workload that can go from scale from top to bottom on this chart. When we look at the AI application specifically for the edge, the cloud always has patterns where you are running a REST endpoint to enable processing or inferencing, but the data collection and data preparation always happens outside of that VM or outside that container. But when you're running a workload on the edge, you are essentially doing everything in one place. You are preparing the data, you're capturing the data. Data can be images, audio, it can be environmental temperature, humidity, et cetera. And then you are running an inference workload and then doing some kind of post-processing on that inference result before you share the telemetry to the cloud. Or you may fire a retraining. So in this pattern, you would have multiple options of enabling that application. You could run all of this in one single container, which can simplify your application. And typically, you do that when you have smaller devices where you have only the space to run or the capacity to run only one container. It simplifies your logic, but it also limits how you can scale. The other option could be where you're running these workloads or these processes in different containers. You may have a container which is processing video streams from multiple webcams in a centralized way, and then you have an inference endpoint which is local to process any of the inferencing query, and all of that can happen asynchronously. This enables you ability to get things in a modular way. You can have the image processing piece done in a different code base or different process as long as it's a container. And then your AI container can be built by your data science team, which is only focused on building an inferencing workload or inferencing process. What I show you here is how we think about building this. Okay, well, the arrow is showing there, not in mine. So when you have a single container, you are essentially looking at your trained model, converted to ONNX, and packaging it with ONNX Runtime. What I show here is the ability for you to use the ONNX Runtime interface with the different execution providers to then query and manage the connection to the different hardware-specific components that are on your platform. If your platform is only capable of executing things in CPU, then ONNX Runtime will know that because of the interfaces it has on the container to execute that graph only on the CPU. versus a device where you may have CPU plus GPU, which then ONNX Runtime allows you to then execute or accelerate the models on GPU. This is an example where you have multiple containers, and this is using essentially a similar logic, but only thing here is that the camera processing module, which is a pre-processing module capturing the web camera stream, is then sending the images over HTTP, or you can also use gRPC, to your inference endpoint, which is then doing the processing and then sending out the data back to your post-processing. This is, by the way, using Azure IoT Edge, which is the infrastructure that we use to communicate with edge devices from Azure. And then my last slide here is that you can get started on this. There is a tutorial published on GitHub. And this is the multi-container sample code that is using the Jetson Nano with ONNX Runtime to enable us to show how ONNX Runtime can be used on edge devices. This was done in conjunction and collaboration with the Microsoft Garage team. And I'd like to bring Kitty over here to give you a quick introduction on what the Garage does and how you can work together with the Microsoft Garage.
Thank you, Manash. So thanks for being here. Just the last couple of minutes, we want to introduce to you about the Garage and how you can work with us and how you can work with Microsoft. So we are a program that drives a culture of innovation at the company. And we serve several audiences. We support our employees who have great ideas. They can always come to the Garage and hack and build their solutions. We support them to push their ideas out. And the teams, such as Manash's team, we also collaborate with every single business groups in the Garage, in Microsoft, and help them ship their projects. And then we also work with our customers. When our customers have ideas, they can come to the Garage and hack with our business teams. And we are a global team, about 20 people globally, 7 locations. We are currently serving under the CTO's office. And we have been running the world's largest private hackathon. This year, we had 27,000 people participating. We invite our customers and partners to our hackathon. So if you are interested in participating in our hackathon, that's every July. There's a slide at the end. You can reach out to us via email. And we also work with our ecosystem, with the schools, and we have internship program to bring new talents to support our ideas and our customers' ideas and business teams. And then we use the experimental outlet to ship those ideas out. So if you go to the Garage website, you will find like more than 100 projects already in the market, and we use that to test out, and some of them actually turn into business features and products of Microsoft. And we do a lot of storytelling, so you find us on news articles and social. So if you are interested in participating in the hackathon, we have opportunities. And in February, we are also planning to run a hardware symposium, hardware sharing of our partners' stories and your solutions. So if you're interested in any of these, you can reach out to us or come after this to talk to me. Thanks.